Hello YouTube! We're back for another video, and this time we're considering equivalence relations. So if you would like to know more about equivalence relations, then stay tuned. Okay, so let's consider these problems. So last time we had drawn a directed graph from this set of relations. And it turned out to look like this. Okay, so remember what an equivalence relation is. Let's have a look. Rho is an equivalence relation if it is reflexive, symmetric, and transitive. Okay, what was symmetric? Symmetric if for all x and y in A, x is related to y, if and only if y is related to x. Reflexive, for all x in A, x is related to itself. And transitive is down here, for all x, y, and z in A, if x is related to y and y is related to z, then x is related to z. Alright, so we need to, in order to do the next exercise, we need to check what we need to include in this set of relations such that this directed graph depicts an equivalence relation. Okay, so you see we're missing 3 going to 3, for example. Right, now let's have a look at what this says. Include additional relations in R, forming R' to make R' into an equivalence relation. Okay, so that's what we're going to do. So scroll this up, come back and open up Mathematica. Alright, so what do we need in order to make this reflexive? Well, we're missing 3, 3. Okay, so I'll go up here and I'll include 3, 3. So 3, 3. Now let's have a look. Okay, now we have 3 going to 3 in our relation and directed graph. Okay, that's not all we need. So now we have this relation being reflexive. We need it also to be symmetric. Symmetric. So we need another arrow going back the other way, much like this 2 and the 1 relations. Okay, so we need it here. We need 1 going to 4, and we need, well, a few more. Okay, so let's include 1 going to 4. I'll put it right in here, 1, 4, and let's have a look. All right, that's better. Now we also need 4 going to 3. So let's include that right here. 4 going to 3. All right, so now it looks to be symmetric. Now what about transitive? So have a look here. 3 is going to 4 and 4 is going to 1, but we do not have 3 going to 1, so we need to include 3 goes to 1. So we'll put that in here. 3 goes to 1, and let's have a look. Okay, now this is our new directed graph. So we've got 1 going to 4, 4 going to 3, and we need 1 going to 3. Okay, so let's include 1 going to 3. All right, that looks good. Now we've got more to do. So look, we have 2 going to 1 and 1 going to 4. So we must have 2 going to 4. Right, so 2 must be related to 4. So let's include that. 2 is related to 4. All right, shift and enter, and let's have a look. Okay, this is almost looking transitive, but we have more to do, you see? So 2 goes to 4. Well, look, I mean, now it's not symmetric. We need 4 going to 2. So let's include that. 4 goes to 2. Okay, now it looks symmetric. All right, but we are working on making this relation transitive. All right, let's see. Are we missing anything? So we have 3 going to 1 and 1 going to 2. Do we have 3 going to 2? Well, no, we don't. So we need to include that. 3 goes to 2. Shift and enter. Okay, now it looks like I need to make this a little smaller so you can see it. All right, and I'll pull this down and this down. Okay, now we have the last thing we put, which was 3 going to 2. 3 going to 2. So that's across here. Now it's not symmetric anymore, so we need 2 going to 3. All right, so we must include 2 going to 3. 2 goes to 3. Shift enter. Okay, this diagram looks symmetric. Okay, now we ask again, is this transitive? So we have 4 going to 3, 3 going to 1, 4 going to 1. Okay, good. 2 goes to 4, yes. Look, to me, this looks transitive. Okay, but it often takes a bit of time to study before you can be sure that you have a transitive directed graph and relation. All right, so I think this is now transitive, but you want to properly check that. Okay, so given that we think that we have reflexivity, symmetric, and transitive, it seems like we have an equivalence relation. All right, now the next thing of importance when you have an equivalence relation, note that it induces a partition on A. Okay, it induces a partition on A. So that means that it breaks up the set A into a set of classes. Okay, so in this case, the partition induced by this equivalence relation is actually the whole set A, because 1 is related to 3, which puts these in the same class. 1 is related to 2, which puts 1 and 2 in the same class. 1 is related to 4, and that puts 4 and 1 in the same class. All right, so all of the elements of A in this case do belong to the same equivalence class. Now, what is a partition? A partition of a set is a set of subsets such that their intersection is empty and their union is the whole set. So that's a partition. But this equivalence relation partitioned the set A into just A. So there's only one class. Okay, so now let's go on while we're at it to talk about another set. All right, so what if I'm to talk about, so write in comment form, let A be the set of all integers, and let the relation be congruence modulo 3. All right, so in other words, we're talking about remainders when we divide by 3. Okay, so let's just check that this relation is an equivalence relation. All right, so it is reflexive. So what we have is x is congruent, and I'll just put equivalent, okay? Put equivalent. X is congruent to itself mod 3. Right, so it is reflexive. So any integer is equivalent or congruent to itself modulo 3. So reflexive. Okay, now what about symmetric? If x is congruent to y modulo 3, then y is congruent to x modulo 3. So symmetric. All right, now transitive is often a little bit more difficult to demonstrate. So if we have x is equivalent to y mod 3 and y is equivalent to z mod 3, then what we can do is add those. Well, look, we've got to write it in a slightly different way. Then we have x minus y equal to 3 times m for some integer m. And we have y minus z is equal to 3 times n for some integer n. And so that means that we can add those equations, right? So adding, we have x minus y plus y minus z on the left equal to 3m plus 3n. Okay, simplifying. You see the y vanishes there. And what we have on the left is x minus z is equal to 3 outside of m plus n when we factorize the right hand side. So what this means is, therefore, spelling problems today. Therefore, x is equivalent to z modulo 3. Right, so what we have done is established that this relation, equivalence or congruence, is a transitive relation. So transitive. Okay, now what have we done? We have deduced that equiv or congruence is an equivalence relation. Okay, that's what we found out. Now that we have that, we can say this must partition the set of integers into equivalence classes. All right, so let's write. So equivalence classes. All right, just to say that with some brevity. And let's find out what they are. All right, so to do that, let's just do a little calculation. I'll come in here into another cell and I'll just work modulo. All right, mod 3. All right, and what do I want to put? I'll just put m. And then let's tabulate table. M goes from, say, minus 50 to 50, and let's see what we get. All right, so you notice that they cycle through these numbers 1, 2, 0, 1, 2, 0, 1, 2, 0, 1, 2, 0, and so on. Right, that's not surprising. So that means that every third number belongs to the same equivalence class. Okay, so let's find out what they are. Okay, let's put in if the remainder is equal to 1, then put m. And otherwise, let's put something we don't want, say w. All right. So now what do you have? You have, in that range from -50 to 50, you have all the numbers that are congruent to 1 modulo 3. All right, so if we now want to get rid of the w's, we can just put delete cases w, and now we have a nice list of those numbers between -50 and 50 that do belong to the same equivalence class. You know, those that are congruent to 1 modulo 3. Okay, but this set of integers that are congruent to 1 modulo 3, it is an infinite set, right? So you can just see some of that picture here, just some of the picture. Now, if you want to find some other equivalence classes, let's just change this to a 2, and we get another collection of elements belonging to the same equivalence class, those congruent to 2 mod 3. And finally, if we copy this, let's find those that are divisible by 3, and we'll just change this to 0. Shift enter. So up here we find all of the numbers between -50 and 50 that are divisible by 3. Okay, so this is showing you the equivalence classes, except of course not all of them are there because you need to go from -infinite to infinite to get them all. All right, so that's what an equivalence relation is, and that's how well, we see how it has partitioned the set A into equivalence classes. Right, so 30 and 33 are related by the equivalence relation, so they belong to the same equivalence class. And likewise, -26 and -23 are related in the equivalence class, or sorry, equivalence relation, and so they belong to the same equivalence class. Okay, so I think that's enough for now. That was a bit of a long video. I hope you have a great day, and I'll see you later.